Hello, welcome back. Okay, before we get moving on something new here, I want to go back just a second to those equations that we balanced. Let's talk a little bit about that. So you'll remember we balanced this equation. It looked like this: 4BCl3s plus P4 plus 6H2 goes to 4BP and 12HCl. And we said that if you can divide all the coefficients out here by the same number and reduce them down, then that would be a good idea. Can we do that here? We can't. Why can we not reduce these down? Well, because this is a 1. See, I mean, yeah, this is divisible by 2, and this, and this, and this. That's true. But if you can't divide everything by the same number, you're stuck where you are. If this were a 2, see, then I could make that a 2, that a 1, that a 3, that a 2, and maybe this a 6. But it's not. So if everything is not divisible by the same number, you can't reduce it down. If everything is, then that's when you can. So yeah, we're stuck right there. Okay. Well, let's move on. Let's talk about something different then today. So let's talk about types of equations for aqueous ionic reactions. You're going to run into a lot of aqueous ionic reactions, in this course, and also when all of Chem 2 is pretty much aqueous solution type stuff. So yeah, you're going to see this a lot, coming up. So it's worth learning now. There are 3 different types of equations we can use to express the reactions. And so let's talk about them. Each of them kind of has their own advantages and disadvantages. Each one tells you a certain amount of information. So let's talk about the molecular equation first. Okay, the molecular equation shows the reactants and products as if they were undissociated. Does that mean they are undissociated? No, they might be, they might not, but you pretend like they're still together. So for example, here is, this is iron 3 chloride. I know that you know why it's iron 3 chloride, because you know how to name compounds. That's soluble, so this is aqueous. Plus 3 potassium hydroxides, that's aqueous as well, that's dissolved in water. When those will come together and form 3 potassium chlorides, aqueous, and iron 3 hydroxide, which happens to be a solid. It's not soluble. We'll talk about why in a little bit. It just is for now. All right? Okay, this is a molecular equation. All right? Does KCl actually float around as little KCl molecules in solution? No. Soluble salts, ionic salts, will break apart into their ions. Okay, so this doesn't actually exist, but you write it as if it did. Now, why would I want to do something like that? Well, because sometimes it makes it easier for this equation to see what's going on in your particular equation. So, for example, this is an example of what we call a double replacement or a metathesis reaction. So I've got a cation here, and I've got an anion here. In fact, I have 3 anions here. Okay, and that's what keeps them together, that opposite charge. Here's a cation here, and here's an anion here. So you can think of it, it's kind of like a dance here. You've got your boys dancing with the girl over here, and you got a boy dancing with the girl over here. Okay, so they decide to switch partners. So how are they going to do that? Are boys going to dance with boys? Not in Texas. Okay, maybe elsewhere, but not here. Boys dance with girls, right? And girls dance with boys. So this cation here is going to go with this anion. And this cation here is going to go with that anion there. All right, and so when it's all said and done, I get 3 potassium chlorides, and I get iron 3 hydroxide. And that's called a double displacement or a double replacement reaction. Sometimes you'll hear it called a metathesis reaction. The nifty thing about molecular equations is sometimes it's easier to see what's going on if you write it that way. All right, even though technically that's not what it looks like. So what does it look like anyway? Well, that's where the total ionic equation comes into play. The total ionic equation shows you all of the ions and all of the molecules in solution exactly the way they are. So if I wanted to write this equation here as a total ionic equation, I know that this is aqueous. This breaks up. And so really what I have floating around is iron 3 plus and 3 chlorides. I know this is aqueous, so this breaks up. And so I've got 3 little K pluses and 3 little OH minuses. So really I have all 4 of these little ions all bouncing around inside the beaker, just floating around. All right? When they react, The iron reacts with the hydroxide. That forms something that's insoluble, so it stays together and goes to the bottom of the beaker. Okay, that's a solid. The potassium and the chloride, when they come together, they still form something that's soluble, so therefore they still stay apart. So basically, to get from here to here, if it says aqueous, break it apart. If it says solid, keep it together. That's pretty much, in a nutshell, how it works. All right. This is a more accurate picture of what's actually going on than this. So why don't I just write this? Well, total ionic equation, sometimes it's kind of hard to see the forest for the trees. There is such a thing as, I guess, too much information. And so if you see all these ions just kind of out there in a big giant equation, you can't really see what's going on. You can't see that this is reacting with that and that's reacting with that. It's easy to see up here. And so sometimes this is easier for people to understand what's going on, or more clear when you're understanding what's trying to happen here than showing everything. All right, but sometimes you want to see everything, and that's kind of what you see right here is everything. And that's called the total ionic equation. Basically, if it says aqueous, break it apart. If it says solid, keep it together. That's what it kind of comes down to. All right? Something that's kind of in between is something called the net ionic equation. And in the net ionic equation, what you show is you only show the ions and molecules that are actually reacting. In other words, you just show what needs to be shown. So how do I get from a total ionic equation to a net ionic equation? Well, it's actually pretty simple. What you do is you look at your total ionic equation. If you see something on the left-hand side of the equation over here, and it's exactly the same on the right-hand side of the equation, you cancel it out. If it's different, you leave it in. So if I want to get to the net ionic equation from this, here's 3 chlorides here, but here's 3 chlorides here. So if I started with 3 chlorides and I ended up with 3 chlorides, guess I didn't use them, right? So what we're going to do is we're going to go ahead and cancel those out. All right, here's 3 potassium pluses. Here's 3 potassium pluses. So I'm going to cancel those out. Here's 3 hydroxides, but notice there's no hydroxide over here. That's changed. So see, that stays in. Same thing with the iron. So we're going to write down everything we have left over here on the left-hand side and everything we have left over on the right-hand side, and we come up with something that looks like this now. Iron 3 plus aqueous plus 3 hydroxides aqueous yields iron 3 hydroxide solid. And that is the net ionic equation. All right? The nifty thing about the net ionic equation is it doesn't show you everything, it just shows you what's important. And so you can kind of key in on what's important. All right, you might say, well, why would I ever want to do that? Well, you do it all the time. You may not realize it. Let's say, for example, you're doing a chemical reaction in lab, and you've got probably a little bit of sodium in that water from the deionized water. Maybe you can get all the sodium out of there. Maybe a little bit of chlorine. But you don't write that in if it's not reacting. You just kind of leave it out because it's not doing anything. It's sitting in there just kind of floating around. So it's extraneous information. So yeah, you actually write more net ionic equations than you think you do. But that's how that works. All right. Like I say, each of them have their own advantages and disadvantages. The total ionic gives you the most amount of information, but sometimes can get a little bit complicated, and so a little unwieldy. The net ionic equation just tells you just what you need to know. So sometimes we want this, but sometimes this is what they're after, is just the net ionic equation. It just kind of depends. If I gave you a molecular, could you give me the total ionic? If I gave you the total ionic, could you give me the net ionic? Okay? All right. Well, those are 3 types of equations for aqueous ionic reactions. These are 3 types of aqueous ionic reactions that you run into. Does every reaction fall into one of these 3 categories? No. Do quite a few of these reactions fall into these 3 categories? Yes. So if you understand these 3 categories of reactions, it will go a long way to covering a lot of chemical reactions that you run into. So where are we going to start? Well, let's talk a little bit about precipitation reactions. Okay, so what is a precipitation reaction? What is precipitation anyway? Well, strictly speaking, precipitation means something more dense fell out of a less dense media. All right, so when the weatherman says, yeah, we got an inch of precipitation last night, what he means is something more dense, like water or ice or snow or mud balls or whatever comes out of the sky out here, hail mostly, fell out of a less dense media, air, which of course is a gas. All right, so it's just a fancy way of saying it rained last night. In chemistry, when we talk about precipitation, generally what we mean is something more dense, a solid, fell out of a less dense media, a liquid, like water. All right? So when you see two solutions that are clear, now when I say clear, I don't mean colorless. You know, it's possible to have a solution that's blue, but you can see through it. Okay, so that's clear, but it's not colorless. We mean not opaque. You can see through it. If you have two solutions, you pour them together, and all of a sudden it gets really, really cloudy. And if you wait long enough, stuff starts settling down to the bottom of the beaker, and you see a little solid down there. You know, it might be white, might be orange, might be green, who knows? You know, that's what we call a precipitation reaction. And that solid is what we call a precipitate. All right. To predict results in precipitation reactions, you have to know your solubility rules. In other words, you have to know what things are soluble in a water solution and what things aren't soluble in a water solution. To help you know that, here are your solubility rules, and these are found in Table 4.1 on page 183. So that would look a little something like this. This is on page 183 here, so we'll take a look at this real quick. There was a time back in my younger days where I actually made you memorize all these solubility rules. Am I going to make you do that? No, I'm not. What I'm going to do is I'm going to go ahead and give you the chart, but you just have to be able to use it. All right? So these are your solubility rules. All right? If you see a group 1 cation, that's lithium, sodium, potassium, rubidium, cesium, francium's rare. You don't run into that really. So probably those three right there. If you see a group 1 cation, always soluble. Those are always soluble. So once you see a sodium salt, for example, you don't even care what the anion is, you know it's going to be soluble. All right? If you see a halogen, if it's a fluorine, fluoride, for example, fluorides are, no, I can't say that. Okay. If you see, let's skip the halogens for a second. If you see an acetate, or you see a bicarbonate, hydrogen carbonate here, or a nitrate, or a chlorate here, usually the acetate and the nitrate are pretty much the most important ones there. Those are always soluble. Okay, if you see an ammonium salt, NH4+, those are pretty much always soluble as well. So group 1 cations and ammonium, always soluble. If it's a nitrate salt or an acetate salt or citrate salts, you know, if you ever run into those are pretty much always soluble. All right? Everything else is either usually soluble or usually not soluble, and that's where it gets real tricky. You know, not everything in life is always black and white. All right. So what are the ones that are kind of tricky? Well, if you see a halogen, if you see a chlorine, bromine, fluorine, iodine, something like that, generally speaking, those are soluble. Okay, but there are exceptions to the rule. The exceptions to the rule here are mostly, we won't get too far afield into it, your heavy metal halides, basically. If you see silver, or you see lead, or you see mercury, okay, with a halogen, those are insoluble. Okay, anytime else you see them, they're soluble. So halogens are generally soluble except for your heavy metal ones, silver, lead, and mercury. Okay, Sulfates generally soluble. Your heavy metal sulfates tend to not be soluble, and your group 2 sulfates generally are not soluble. But you know that's what this is. These are exceptions over here. Okay? And then most everything else are generally insoluble with certain exceptions. Okay? So you've got carbonates, chromates, phosphates, sulfides. You know, these are generally pretty much always insoluble. Hydroxides are generally pretty much insoluble, except, okay, with these 4 up here, if you see a group 1 or NH4+, it's soluble. Okay, because all group 1 salts and ammonium salts are soluble. Okay, but if it's anything else, insoluble. Hydroxides, if it's a group 1 salt, it's insoluble. Excuse me, it's soluble. Also, your calcium and your strontium and barium, your group 2, calcium on down. Those tend to be soluble. Group 1 hydroxides and group 2 calcium on down, those are going to pop up again here in a few minutes. And those typically tend to be soluble. If it's any other hydroxide, it tends to be insoluble. All right? So all you have to do, you don't have to memorize all this. All you have to be able to do is use the chart. I would give you the chart on a test. All right? But on an ACS exam, if you're doing like some sort of national, ACS exam, something like that, they generally don't give you the chart. So, there's only so much you can do. You can't memorize every exception to the rule. But what I would do is just remember group 1 salts and ammonium, always soluble. Nitrates, acetates, citrates, always soluble. Sulfates generally tend to be soluble, exceptions to the rule. Halogens, chlorine, fluorine, bromine, iodide, generally soluble except for your heavy metals, your silver, lead, and mercury. And then the rest of them generally tend to be insoluble. Exceptions to the rule would be your group 1 and ammonium, because those are always soluble. And then hydroxides typically tend to be insoluble except for group 1 and your heavier group 2. And that would be calcium on down the periodic table. Are you going to remember that sulfates are generally soluble except for barium and calcium and, silver and probably not. Are you going to remember, well, iron chloride's insoluble, along with that? Probably not. If that comes up, I guess you just missed it. I mean, you can't memorize everything. You can only do so much. But, I think you can generally remember all nitrate salts are soluble, and, so are acetates, and your group 1 and group 1 salts are always soluble. I think you can remember that. So if they ask you something like that, which is probably more than likely what they do, you're probably going to be okay. But on this test, I will give you the chart. All you have to be able to do is use the chart. Okay? So, a little practice here. Let's say I'm dealing with iron 3 carbonate. Soluble or insoluble? Well, here's carbonates. Carbonates are generally insoluble except for compounds with group 1 and ammonium. Is iron a group 1 or ammonia? No. So therefore, iron 3 carbonate would be insoluble. Okay. Sodium hydroxide, soluble or insoluble? Well, that would be soluble because most hydroxides are insoluble except for your group 1 cations. And sodium is group 1, and we know that all group 1 salts are soluble. Okay? How about calcium sulfate, soluble or insoluble? Well, I know that most sulfates are soluble except silver, barium. See, there's calcium right there. So therefore, we know that this is insoluble. So all you got to be able to do is read the chart. If you can read the chart, you're going to be okay. Not gonna make you memorize the chart. Okay? All right. Well, if you can do that, now you can actually start predicting results for precipitation reactions. So let's talk a little bit about that then. All right. So mixed solutions of barium nitrate and sodium carbonate. What happens? Okay, now, if I got a solution of barium nitrate and sodium carbonate, I know they're soluble. Otherwise, I wouldn't have a solution of them, right? But just for practice here, why is barium nitrate soluble? Well, because I know that all nitrates are soluble, see? So that's got to be soluble. Why is sodium carbonate soluble? Well, most carbonates are insoluble except for, here's your group 1. See, there's your sodium. That's in group 1, so I know that's soluble. So yes, these are both soluble, which I wouldn't have a solution if it wasn't, right? Okay, but what happens when I pour them together is the question. Well, here's how we're going to kind of approach this. What we're going to do is we're going to say, okay, first thing, what do I actually have floating around in solution? What do I have that could actually possibly react together? Well, I know that when I put barium nitrate in water, I know it's an ionic compound. I know it breaks apart into its ions. Okay, so I've got barium 2 plus here floating around, and I've got some nitrate. Now I know I've got 2 nitrates here, but at this point, I don't care about how many. I just care about what. We'll take care of the how many here in a minute. Okay, so I got some barium, got some nitrate. Okay, sodium carbonate, when I put that in water, what does it do? Well, it breaks apart to give me 2 little sodium pluses floating around. So I get some sodium plus. And remember, your polyatomic ion still stays together here. You know, if I have 2 of these, they'll break apart. But this carbonate stays as a carbonate. So you got to know your polyatomic ions. You got to know, hey, that CO3 is a carbonate. It's got a -2 charge, and it's going to stay together. Okay? So imagine a beaker, and you've got these 4 little things all kind of floating around, bouncing around all over the place. Okay, inside that water solution. Okay, second thing we're going to do is we're going to figure out, okay, what could possibly happen here? What are my possible precipitates? Okay, well, I know that a barium and a nitrate are not going to come back together, because as soon as they come back together, they'll just split right back apart. No net reaction, see, because I know that barium nitrate is soluble. Okay, would a barium 2 plus react with a sodium plus? Well, no, because they're both positively charged. See, and like charges repel, they don't attract. So, you know, that's not going to work. Nitrate, carbonate, same thing. All right, so really there's only 2 possibilities here. Okay, a barium could react with a carbonate, and my sodium could react with my nitrate. Okay? Remember, when you write the formulas for ionic compounds, they have to be neutral. If they're not neutral, you've done it wrong. So I've got a barium 2 plus and a carbonate 2 minus here. What's the smallest number of those I can put together and get something that adds up to 0? Well, one of these at +2 and one of these at -2. +2 minus 2 is 0. And so the formula for barium carbonate is BaCO3. Okay? Sodium and nitrate. Sodium's +1, nitrate's -1. What's the smallest number of these I could put together and get something that adds up to 0? Well, one of these and one of these, and so the formula for sodium nitrate is NaNO3. So you got to know your polyatomic ions. If you don't know your polyatomic ions, you're not going to be able to write formulas. It's kind of important. All right? Next, what we're going to do is we're going to say, okay, what we formed, is it soluble or insoluble? Because if it's soluble, as soon as it comes together, what's going to happen is the water is going to split it right back apart, and you're right back where you started. See? But if it's insoluble, as soon as it comes together, the water can't pull them apart. Okay? And so therefore, it's going to stay together, and they're going to settle out to the bottom of the beaker, and you're going to find them laying on the bottom of the beaker as a solid. All right? So here's where the solubility chart comes in. So we look at barium carbonate, and we say, okay, soluble or insoluble? Well, I know that most carbonates are insoluble, except for group 1 and ammonium. Is barium a group 1 or ammonium? No, it's group 2. So therefore, insoluble. That's where we got that from. Okay? How about sodium nitrate? Soluble or insoluble? Well, that's definitely soluble, because I know what? All group 1 salts are soluble. I also know all nitrate salts are soluble, so it's soluble for 2 reasons. So that's what the S is there for. Okay? So Net Ionic Equation up here, by the way, you know, how did I know to put an S after this iron 3 hydroxide? Well, look at your solubility rules here. Most hydroxides are insoluble except for group 1 and your heavier group 2, calcium on down. That's not a group 1 or a heavier group 2, so that's how I knew it was a solid. All comes back to your solubility rules. Okay, well, back to this. Okay, so now that I've got this, I can write the Ionic equation. So how am I going to do that? Well, I started out with barium 2 plus and 2 sodiums and 2 nitrates kind of floating around. We just put the 2 there to kind of make the make my equation balance here. Here's my carbonate. So here's where we're taking into account how many. Okay, when it's all said and done, the barium carbonate came together and stayed together, so it's a solid, and the sodium and the nitrate broke back apart, so it's still aqueous. All right? Well, how do I get the net ionic equation from that? Well, cancel out everything on the left-hand side and right-hand side that's the same. So here's 2 sodiums, there's 2 sodiums, there's 2 nitrates, there's 2 nitrates. What am I left with? Well, I'm left with barium 2 plus carbonate goes to barium carbonate solid. And that is the net ionic equation. What would I see if I actually poured these together? Well, I'd see 2 clear solutions. Sodium nitrate I know is colorless and clear. Barium, sodium carbonate is. Barium nitrate I think is also colorless. As soon as you pour them together, it'll get cloudy. And if I remember correctly, barium carbonate is a white precipitate. And so it'd get really kind of white, cloudy, chalky looking. And if you let it sit there long enough, it would settle to the bottom of the test tube or the beaker. And that solid would be barium carbonate. See? And you can actually predict that before you even start mixing things together because you know something about solubility. Make sense? A nice handy little shortcut here, because usually they're just interested in the net ionic equation, is if you see a solid forming somewhere in here, this insoluble here, just write a balanced equation for formation of the insoluble, and that usually gets you there. You don't have to go through this step here and cancel if you want to. If both of them are insoluble, then you'll have 2 solids over here. Write a balanced equation for the formation of both of them, and that's kind of the way it works. All right, you want to see one more? All right, let's see if you can do this one. Mix solutions of barium chloride and sodium hydroxide. What happens? Okay, so first thing we're going to do is we're going to figure out what ions do I have present. So I know the barium chloride, soluble. Most chlorides are soluble except for your heavy metal chlorides. But I know this is a solution, so I know it's got to be soluble. Breaks apart to give me Ba2 plus and 2 chlorides. So I've got some barium 2 plus, and I got some chloride floating around in there. Okay, sodium hydroxide. Of course, it breaks apart to give me Na plus and OH minus. All group 1 salts are soluble, so sodium salts are soluble. So there's my Na plus and my OH minus. Okay, then I figure out the possible precipitates. What could possibly happen here that's different. Well, this barium could meet up with this hydroxide, and this sodium could meet up with this chloride. So the formula for barium hydroxide is BaOH2, because this is a plus 2, this is a minus 1. So I need 2 of these little guys here to balance out this plus 2. Writing formulas, BaOH2. And then sodium chloride, plus 1, minus 1, so just NaCl. Okay, then we go to the chart, and we see what's soluble and what's insoluble. Barium hydroxide, soluble or insoluble? Well, most hydroxides are insoluble except for group 1 and your heavier group 2 hydroxides. This is a heavier group 2 hydroxide. So barium hydroxide would happen to be soluble. All right, how about sodium chloride, soluble or insoluble? Well, I know that all group 1 salts are soluble, all sodium salts are soluble, so sodium chloride salt would be soluble, which of course you probably knew that before you saw the solubility chart there, right? Okay. So now we're going to write the Ionic equation. So what do I have floating around in here? Well, from the barium chloride, I've got Ba2 plus and 2 Cl minuses. From the sodium hydroxide, I've got 2 Na pluses and 2 OH minuses here. Okay, and then when it's all said and done, my barium 2 plus is still there because when this comes together, it splits back apart because it's soluble. My hydroxides are still there. My sodium chloride splits back apart, so my sodiums are there and my chlorides. Okay, how do I get the net ionic reaction? Well, we cancel out everything that's the same on both sides. So here's a barium, there's a barium, there's 2 chlorides, here's 2 chlorides, here's 2 sodium pluses, here's 2 sodium pluses, and here's 2 hydroxides, and here's 2 hydroxides. So what am I left with? I'm left with nothing. Everything canceled out. So what does that mean? Well, that means there's no reaction because you have nothing left. There is no net reaction here. What does that mean physically? Well, if you took a solution of barium chloride and a solution of sodium hydroxide, both of them would be clear because there's no solid in there, and you poured them together in the same beaker and stirred it around, what you'd end up with is another clear solution. Because no matter which ions bounce off each other and hit together, nothing forms an insoluble salt. They just break back apart. So instead of two solutions with two ions, different ions floating around, I've got one solution now with 4 different ions floating around, but I have no solid, and so therefore no reaction. All right. If you see stuff on the left-hand side and all of a sudden you see a solid forming on the right-hand side, that's a precipitation reaction. Dead giveaway that that's a precipitation reaction. All right. If I gave you solutions and mixed them up, could you tell me what happens here if I give you the solubility chart? Okay. All right. Well, that's not a bad place to stop, I guess. So we'll quit there for now. That's about 30 minutes. We'll talk about the second type of reaction you run into, which are acids and bases. Acid-base reactions, extremely common. A lot of the second semester we'll talk about acids and bases. We will talk about them in such excruciating detail you will be begging me to stop talking about acids and bases when it's all said and done. So we'll introduce that, and I guess we'll talk about the third type of reaction and go from there. So I guess we'll see you next time. Bye for now.